In the circuit below, the load impedance CL absorbs 3,500 real watts and absorbs 4,500 imaginary watts. The sinusoidal source delivers 9,800 real watts. So we can see that as 9,800 watts plus JQ. We don't know what Q is. I'm going to put T for total. And ZL absorbs 3,500 watts, and it also absorbs 4,500 VAR. And we notice absorbs is the standard word used for real wattage, and when it's used in imaginary wattage, it's also addition both times, and so it's easy to remember that absorbs both times is positive. The only real component in our line is 12 ohms, and so we can solve using our real wattage from the source is equal to the sum of our line and load wattages. And so if we move one over, we would get subtracting 3,500 watts is equal to the wattage of the resistor P. And so we can now say 6,300 watts is equal to P line. Power for the line is equal to I RMS squared times R, which in this case is 12 ohms. So now we have I RMS squared. We take the square root of both sides, get just I RMS back, which is essential because I RMS VRMS is power. And for our imaginary side, we will also need theta because the imaginary side is SJ sine theta. And so we can find theta using a very simple rule that V RMS I RMS is equal to cosine theta is equal to 9,800 watts. And so if we divide both sides, we get 9,800 watts over V RMS I RMS, and then take the arc cosine to get theta all by itself. Now with theta, we should be able to find our imaginary part. What we can do here is we can say that 9,800 watts over cosine theta is our real part times sine theta for our imaginary part is equal to a number QT. And so we can now use this number because we have all of these things. We can also simplify this and say tan theta, because that's the definition of tangent. And so now that we have QT, we can say QT minus the imaginary part, 4,500 VAR, is equal to Q line. Once we have Q line, we would take Q line and we would say JQ line is equal to I RMS squared times Z, which is negative J omega C. And we would get Q line. To solve for C, we can get rid of the J's because they'll divide out. And we find that C is equal to I RMS squared over Q line times omega. And then because J comes out, we have a -1 here. C can never be negative, and so when we solve for Q line, we'll actually get two versions of Q line, because over here at cosine theta, this is going to give us something between 0 and 180 degrees. And because of the way cosine works, it could also be anything -1 times that. And so we'll take the negative number that we receive, or the negative theta that we would need, and plug that into tangent. We would actually receive a negative number, and that would actually give us the proper Q line to use, so that -1 cancels out, and we get our C. For omega is equal to 2 pi f. And we received 100 hertz as our frequency in the problem statement, and so we can use 2 pi f to solve using omega, and now we have every variable here. I think that's the simplest way to solve this problem, and if we were able to use a little bit more time, we could plug that into the calculator and get the answer that we're given in the back of the homework for homework 9, and it would work. So